Good. Okay, thanks everyone for joining us. Today we have Phillip Lippe giving us a talk. He's a PhD student with Stratus Garbus and Tucker Cohen at the University of Amsterdam, and has done a whole bunch of awesome work in the causal representation learning space in from with a whole bunch of people, great people at the University of Amsterdam, so beyond Tucker and Stratus. He's also responsible for one of the nicest deep learning courses out there. University of Amsterdam's deep learning course with Stratus teachers. I think Phillip was responsible for making almost all the course notes, and they're a really fantastic resource if you want sort of a modern deep learning course that has code and everything. And I think they're linked on PyTorch Lightning these days. Am I right? Or PyTorch Lightning links to those courses.
Yeah, should be.
Yeah. Cool. And today we're going to have Sebastian Lachapelle giving the discussant slide as usual. The discussant just is the role of these slides is just to kind of contextualize what we've seen so far. Well, this work in what we've seen so far. House rules questions I think are fine. Phillip, if either raise your hand or ask a question in the chat, and I'll pause Phillip. And if you can turn your camera on, that would be great. Keep yourself muted, but so Phil's not talking to an empty room. Cool, Seb, you can go ahead.
Right. Okay. So in this series so far, what has been covered is essentially this different instances of this generative model where you have a latent vector z and a generator g that brings z to some high dimensional observation x, and essentially I think maybe the general principle here is that we want to constrain this model in some way to obtain identifiability of the latents up to some equivalence class, like for instance a permutation or something like this. And so like two things that we can constrain here is either the distribution pz or the mixing function g. And we saw a few examples of this where, for instance, you can either constrain the you can assume that you have access to interventions on the latents, so that can be useful for identifiability. You can also assume, for instance, a polynomial declutter for your generator G. You can also make sparsity assumption on the generator, and all sorts of different combinations are possible, and we saw examples of that in this series. And so now what we're going to do today with Phillip, if I can change my slide, okay, is we're basically going to consider a temporal setting where essentially we have temporal dependencies between the z's, and essentially we have a decoder g that sort of maps z to x at each time step. And in BISCUIT, what we have is essentially like a regime variable, which is similar to the auxiliary variable that we have in like the nonlinear IC literature. And my understanding of the idea here is that we will sort of constrain the influence of this regime variable in a very specific way. Basically, this R variable would be sort of mediated by a deterministic binary vector. And of course, like Phillip will explain this, will correct me probably during his talk. And also, like in their paper, they have like very nice practical applications, which I think are very needed in this field, which is maybe a bit more theoretical. So so yeah, I think that's it. Maybe Phillip, you can go ahead. I'll stop sharing.
Perfect. Thanks so much, Seb, and also Jason for the introduction, and yeah, for inviting me. Actually, it's also quite accurate what you said, Seb. So this is indeed like our whole idea of this paper was actually to see what are like practical assumptions that we could take in environments that we also work with. And one thing that we will do is basically take here the assumption of like having binary interactions, and what that precisely means. That's basically what this talk will be about. So let me first get started with a bit of a problem setup. Like I think everyone here already knows a bit what causal representation learning is about. But specifically what we consider here are like environments that are interactive. So meaning, for instance, you have an agent that can perform actions on some environment and you get basically a high dimensional image back. And essentially this would feed back to the agent, and based on that, the agent could decide what to do next. And generally what we also do, like outside of causal representation learning, would be probably first to learn a representation, because we start from very high dimensional data, but generally we probably want to take decisions on much lower dimensional. And one motivation also behind like probably why causal representation learning a bit is interesting for IL setups is then to also ask what representations are actually here the best. And one way of eventually answering is, well, if you're interested in also potential tasks of basically saying, okay, I want to influence only certain variables, it is good to know actually what are like causal variables here and how do they interact. And therefore, one motivation why, for instance, causal representation learning could be helpful is essentially exactly this setup. So in the previous talks of the series, we have seen already a bit of causal representation learning, but let me first also be a bit clearer in what we mean now in temporal causal representation learning. So we have here basically a video or basically sequences of images. And what we want to do is to go from these images to basically a representation which identifies different causal variables. Like in this environment, you could say, okay, you have a microwave, whether it's open or not, whether it's on or off, the egg where there's a potato, stoves, and basically they can all interact with each other. And since we're in a temporal setup, how we usually say it is that, well, you have it at a time step t, but also at the next time step, you have like the same causal variables, but they all change their values. And they change the values in basically influencing each other, like the microwave can cook a potato, the egg can also get cooked, for instance, by the stove, and so on. So essentially what we want to do is we want to learn these causal variables as well as how they interact over time. And additionally, what we a bit consider in this environment is specifically there's probably an agent that can also influence these causal variables, but basically without really knowing what it's doing. Like if you have a random policy of just doing random things, it will probably in some way always influence the causal variables, but we just have no idea how. To be also a bit more formal, so basically temporal causal representation learning is also coming from the idea of dynamic Bayesian networks. So essentially you can represent them here on the left, which is essentially you have a time step t-1 and a time step t, where you define then certain causal variables as well as the interaction between each other. And we basically assume that this is like a template that is repeated over time. So the stationary assumption basically just means we can define this causal graph as here on the left. And what it means, if you would unroll it, basically all these interactions would just repeat over time. For simplicity, I basically just visualize here two time steps. So basically a time step t-1 influences time t. But technically also I think most works and also ours could be easily extended if you say, okay, we have the last 5 time steps or something that can influence it. As long as you still have like a limited frame and basically say this in this everything is Markov, then you can basically also repeat these interactions over multiple time steps. So the task is really to basically find this graph that is defining between all of these time steps. Also one thing that I just want to highlight, because there have been already a lot of discussions on, for instance, how does temporality also connect with counterfactual setups. In terms of temporal, we basically still allow all of these causal variables to evolve over time. So in these environments that I show here, it's essentially just showing you that in a video, like all of these causal variables just interact and change all at the same time. Therefore, we don't really have like paired observation where you could say, okay, between these two, only 1 or 2 causal variables would have changed, but instead all of them follow some mechanism that just goes over time and continues going ahead. So generally, what is the task really what we want to solve? So on the one hand, as already mentioned in what is mainly causal representation learning about, namely to find the causal variables of the environment, but also to find basically the graph, so essentially the causal graph between them. One thing that we add a little bit here is, since we have also here an action information and could potentially want to use these representation for some downstream tasks afterwards, is the question, how could actually the agent now intervene in causal verbals? So while we do initially a random policy, you might be interested afterwards to say, okay, I want to open just the microwave. And one way in our method that we will also show is actually you learn how you could now do actions to intervene on this specific causal verbal while not really intervening on any of the others. Obviously, like causal observation learning and especially temporality is not like the first thing that our method does. So there have been already a lot of previous works, also from Sepp and Jason here, to just show a few. And all of them have been, again, like slightly different setups where they can work and slightly different assumptions to take. The one we want to take here, or why this is basically mainly different, is this idea of having basically non-parametric arbitrary graphs. So we don't really look into how the causal model is in that sense, but we look at the combination of how does the agent actually interact with the system. And we assume here that there are unknown binary interactions. What that exactly means, that's maybe what we look at now. So specifically, our key assumption is that interactions between the agent and any causal verbal can be described by a binary verbal. Why that maybe makes sense is, for instance, we have a time step t, which could be here, for instance, the microwave and the state of it currently. And any causal verbal will probably have some mechanism that we could call observational. So basically, if an agent wouldn't even exist in the environment, this is probably how this causal verbal would progress over time. In this specific case, basically, if a microwave is closed, probably the microwave will stay closed. But there's also a way that now, since we have an agent, some actions might actually now start to interact with this causal verbal. Meaning that eventually, in some interactions, it changes the mechanism of a causal verbal. And in this case, for instance, we would now actually change the state of a causal of a microwave. And this is what we mean that we could describe the action by a binary verbal, meaning that by knowing really what the agent does, so like we just have the action information, there could be a ground truth verbal to say, is the causal verbal observational or interventional in that specific time step? So there are also like more examples. For instance, in the same environment, if you have an object, an interaction could be, for instance, to pick it up, versus no interaction would basically not do anything. But also here to just clarify, like the causal verbs themselves, they don't have to be binary. And all of these interactions can also be stochastic. So in this specific example, we have, for instance, if an agent picks up the plate, it can end up like anywhere where the agent could place it. So there's some randomicity that goes on, as well as the causal verbals, like the position of a plate is still a continuous verbal. And also the observational case, it can be continuous or continue to change. Just in this specific example, it basically stays the same, and it's just the easiest actually to visualize. So to just be a bit more specific, again, it can basically evolve over time, and just these interactions we consider as like unknown interventions that just switch between an observational and interventional mechanism. And we think that this is actually often quite realistic in some reinforcement learning environments. Like you always have basically objects that evolve over time if an agent wouldn't be there, and the agent can in some way interact and change the mechanism. And that way, basically also if you have a reinforcement learning environment with a certain task, if you want to have like a certain object in a certain state, then probably also the agent could probably influence it in some way. And therefore, like this is basically our main motivation, actually, why we considered this setup. Now let's look at a causal graph to also a bit grounded in a bit more theory, how it would look like. So we essentially have, as in any causal observation learning method, we have some observations that we call basically X, that we observe, while there are some ground truth causal variables that we don't observe. So these are our latents. And since we have basically time, we have basically observations at each time step, as well as the causal variables between the different time steps. And these form basically a dynamic Bayesian network. So there are arbitrary temporal causal relations that we probably don't know in the beginning. And what the agent really adds is essentially a regime variable. So this could be, for instance, the action that the agent does. And we represent the interaction of these regime variable to the causal variables by a layer of these eyes, which we call interaction variables. And these are essentially binary. So this is the enforcement where we say these are binary interactions, meaning that the influence of this action or of this regime variable can be described by a binary variable on each of these causal variables. So in our environment, just to also give these variables a bit more insights. So the xt's here would be our images. The rt's would be basically the actions that the agent does. And we are basically interested in finding these causal variables here and eventually also actually identifying these action variables. So in terms of theory, why do we even expect actually that this would help? Because in the end, we don't know the interaction variables. So in some previous work, we've showed that if you would know these interaction variables, which essentially would then give you like interventional targets, you could identify the causal variables. But you don't have them, so why does it even help to assume that there would be like binary variables? One way of a bit motivating it is if we take now the example of an additive Gaussian noise model, where essentially you have a mean evolving over time in an arbitrary function, like here we just called it mu, and you basically just have this additive noise coming on. This is often like a tricky actually situation in whether you can identify it or not, especially if you don't take any assumptions on the mean, because as we are in a Gaussian regime, basically you could rotate without changing really the likelihood. But the idea that now this interaction variable here is binary to switch between like two mean functions does really help you to identify. Because if we would find the two causal variables and would visualize, for instance, under intervention on a causal variable 1, we would probably change the mean of this causal variable. Under the intervention of causal variable 2, we would probably change its mean. And then you have like a joint intervention, which would just change both of them to their respective interventional means. And there you can also see that basically the mean is indeed like binary, like it has two possible values. But now as you start to rotate, for instance, the variables, which before was basically equal likelihood, you see that the number of means that each of these causal variables now take is actually more than binary. For instance, now in ground truth intervention on C2, it's now actually changing both of these identified causal variables. And for instance, now if you also take a joint intervention, it again gives you a different mean. So this restriction of just saying we allow only two means gives you now actually in this specific example, identifiability up to 90-degree and 180-degree rotation. And that basically corresponds to a permutation of the variables or just flipping a sign on one of the two. So like for this specific example, you could already see how it identifies. Daniel?
Yeah, I was just wondering if this two means assumption here rules out the ability of having like interaction effects between the two different latent variables C1 and C2, for example, where like when you intervene on both of them, they still have to map back to their interventional means, and there's not going to be some unique new mean that you get when you do a joint intervention. So is that kind of right, that it rules out sort of interaction effects?
Yeah, actually, the way we rule it out is just by assuming that there are no instantaneous effects. So in the sense of that, like the next time step, let's say C1, I can predict the mean here based on the previous time step, but we actually never need to know like the value of C2 at the same time step. Like these instantaneous effects are actually often like what can break a lot of the temporal causal observation learning.
Okay. Yeah.
But like, yeah, if you would have instantaneous effects, then it would be actually tricky to enforce with binary as well.
Great, thank you.
So basically, besides now the binary assumption, there are also a few more assumptions that we have to take as usual, because basically our previous example, you can easily now show actually you could break it if, for instance, both, or let's go back, if you would only observe this joint intervention on the two variables, but you wouldn't observe like all of these interventions. Because if you would only observe like the joint intervention, you see that, for instance, now in this rotated example, actually you would have two means for one variable, but basically a single mean for them. So one assumption we also need to take is actually that we have enough interactions that cause also enough diverse interventions. So what that just means is that if you have two causal variables that are always jointly intervened or always not jointly intervened, you will be not able to disentangle them. So you will probably have like a block identifiability of the two, but you will not be able really to go beyond that. Interestingly, what comes out if you now try to see, okay, how many values of like different actions, different interventional experiments would I need to have, is that we would still be able to potentially scale with a log of a number of causal variables. So this is basically here a logarithm of the number of causal variables k. So meaning that if you would now have twice as many causal variables, you would probably just need one more experimental setup if you would come from like the intervention design perspective. But whether that really matters so much or not, it's of course also a bit the question, because we assume that we don't even know what interventions are happening. You just have an agent doing random interventions or interactions even. So in general, it's also a bit hard to now actually judge from just, for instance, a visual inspection, do we meet all the requirements of it? Although you could probably say in most cases you will. The third assumption is basically what also Dania, or what the question of Dania really points to, is essentially that we don't allow for instantaneous effects. So meaning all of these causal relations need to be resolved over time, which is kind of a classical assumption behind temporal causal observational learning to make it really work well. So that basically all the causal variables within a time step are conditionally independent given the previous time step. And in our specific setup, you also have to add the action. So basically with the action of the time step and the previous causal variables, basically all of them become conditionally independent. There are some works that allow for instantaneous effects, but then you also need to have stronger assumptions, like for instance, the interventions need to be perfect at least over instantaneous, or you could go also the full scale without temporality, where you often also currently need stronger assumptions on the interventions. And the last assumption, which I don't want to dive too much into detail because that would probably also require a bit more background information on like the theory and how we prove it in a certain way. It's just that to a certain degree, the causal mechanisms also have to vary. So for instance, another counterexample where very quickly you will not be able to identify anything is if the interventional distribution and the observational distribution are actually identical over time. Because when technically there doesn't exist like an interventional distribution, and that would directly break basically anything that we really would hope for. So for that, basically we have to account, and we account for that basically in two ways. Either we have basically like a dynamics variability assumption, where you just need to take a bit more assumption on like how the interventional and the observational distribution differ. So for instance, a Gaussian with like a bit flexible standard deviation would fulfill this assumption, or we would need to take assumption on how it a bit varies over time, so that you cannot basically exploit a certain bias of something always evolving the same way over time. Actually, like the time variability is also something very common in other temporal causal observation learning works. Although in this case, we have it a bit more softer assumption, because for instance, here we only assume like the first derivative needs to be linearly independent, and often actually other works require like second order derivatives as well, which can then sometimes like limit the distributions to apply, like this additive Gaussian noise model. So to conclude a bit like the theory setup, just the four main assumptions we need to take is this binary interactions, that we have enough diverse interactions between them, that we don't have instantaneous effects, and that the causal mechanisms vary at least to a certain degree. And with that, basically, we can show that the causal variables then become identifiable, again, up to permutation and elementwise transformations. Also, this permutation is also a bit more relaxed in the setup, in the sense that if you would give us like some examples of, for instance, in this frame, this causal variable has been intervened, and in this frame, this causal variable has been intervened. What you can do is you can actually start to align like the binary interactions that we have identified in our model with like ground truth interactions that you might have labeled. So with a few labels, you could easily actually get beyond the permutation as well. And with that, basically wrapping up a bit the theory, I also want to spend like enough time on actually showing how you can practically make it work, because often, like at least for me in these papers, I really try to do theory, but also really show that it works on diverse environments, and even also can hold if some of the assumptions will break. Because often in theory, we need to take a lot of assumptions, and in practice, it's rarely that we can really go to like a realistic environment where we say all of the environments precisely 100% will hold. So in practice, basically, we will use exactly like the causal model, as in we have here an observation, and we will want to go back to basically a latent space where we can identify these causal variables, as well as go from like action information to unsupervisedly learn these binary variables. How we precisely do that is basically we just take now a smaller set of, let's say, we have a pair of images, which is exactly this temporality. So this is time step t and t+1. And we have the agent, and then we have given the action that the agent test us. For instance, just a xy coordinate. First, we basically apply an encoder, as usually also in computational learning, to map these high-dimensional images into a smaller latent space. And it's a bit built up as a VAE setup. So you have a decoder to then reconstruct the image to make sure that you can actually reconstruct the image and have all the information in your latents. And we basically have a prior of this time step t+1, which is conditioned on the previous time step. So this follows exactly like the causal model of saying the previous time step will influence the next time step. And now to learn our binary interaction variables, we essentially introduce here a small MLP, which basically takes as input the action and like the previous time step. Also, we often take like the latent representation of a previous time step just to reduce the computation in here. And this MLP will then try to predict a binary variable for each latent in our latent space. So these are basically these binary interaction variables that are unsupervisedly learned. So the MLP will have to basically figure out by itself, based on the prior, which variable will need which of these binary variables, as well as this will actually guide us to disentangle. So to be a bit more precise on the loss function, it first looks complicated, but let's go step by step. So again, we have an encoder, which takes as input basically x as observation and predicts zt. We then have a decoder, which basically maps from zt back to x. And we have then the prior here on the right. And this objective function is essentially a classical VAE. So you have on the left side just the reconstruction term to go into latent space and back. And on the right side is now this prior modeling, which is kind of the key behind the objective, where we contrast our encoding distribution with basically the prior, which is the conditional of the previous time step, as well as the action. And this prior has then basically, again, you can factorize it into, this is basically the temporality assumption that each of the latents will now be conditionally independent based on the previous time step. And what we add here is essentially this binary function output. So this function fi takes as input the RT, like the action of the agent and the previous time step, and we will enforce it to predict basically binary output. So essentially this output is then supposed to be the binary interaction variables in the end. But the most challenging thing behind making it work is how can we now actually get decent gradients through this binary function? Because as we know, if you now have like discrete variables, you need to apply some tricks to at least differentiate through it. During the process of really developing the method, we also iterated over a few that I just want to show to also give you like an intuition what may work and what usually doesn't work. So the first approach that we thought of is, well, you could basically build exactly as we said before. You have an observational mechanism and an interventional mechanism, and essentially at each time step, you just learn a distribution of how likely is that this time step is currently observational versus interventional. So you essentially have like two priors, where then this interaction or predicted binary value would switch between the two, depending on what it needs. What we usually saw, because like you start with a random model, which has two random priors and basically some entangled latents, these two priors very quickly just converge to be exactly the same. And it's very difficult to motivate the model again to push these two priors apart, because it probably just learned this binary variable to be like 50-50. And therefore, usually this model doesn't really converge. So the alternative is just intuition that a lot of people do with discrete variables, namely do a Gumbel trick. So essentially, you take your output, which can be a continuous value, for instance, here specifically like a probability in your sigmoid, you add some noise and discretize it, and then in the backward path, you just use a straight through estimator, so basically pretend your binarization didn't even happen here. But as also like in many other situations with a Gumbel trick, you introduce high variance here, because basically small changes also in your probability can very quickly like jump between 0 and 1, and it's quite a big gap in your model. So we usually saw that like it sometimes works, but even on synthetic data, it has quite difficulties to stably converge to the right solution. So instead, what we found to work best is actually to go like with a full continuous relaxation. So you don't use fully discretization, but you essentially apply a tan h, which enforces the model anyways to be like between -1 and 1. And you apply a bit of a temperature parameter. So you start off with allowing the model to be basically continuous in that frame. But as you reduce the temperature, basically the tan h becomes more and more like a step function until it basically becomes discrete. And with that, like step-by-step or like smooth optimization, you actually allow the model to first find like roughly a disentanglement, and then the enforcing of a binary really make sure that you get to the solution you need.
Phillip,
So this is basically, yeah.
Is tan h important as a point? Like, why would sigmoid not work? Do the same thing essentially?
Sigmoid would also work, like that is not a problem. We just apply tan h because like this value goes into like latent or still a feature in our model. And the tan h has like the nice property of a mean still being 0, while the sigmoid would just give you a bias. Like
Gotcha.
we could also use like a sigmoid and then shift it by 0.5. It would give you the same thing. So this, yeah, sure.
Yes, sorry to interrupt. Could you describe a little bit how the discrete variable is used by the prior? Like, is it just you have like an MLP that takes ZT-1 and a discrete variable, or like do you have an embedding there? Or like how does it get into the prior?
Yeah, that's a good question. So we literally just apply like a linear layer to map this single variable output of a tan h to then the feature dimension of MLP. The only small trick we do is that, well, we still want actually, like for instance, the ZT-1 could be here like 40 or 64 dimensional, versus you have like a single dimension of your action variable. So we just ensure that during initialization, we actually initialize both of them separately, such that we also give like the interaction variable a decent amount of importance. And otherwise, it's literally just the MLP where you just throw in all of that as the input and let the model figure out how it interacts. So basically, I said this is a bit the prior, but one thing that I also want to highlight, which is not necessarily just coming in this paper, but one thing that I often saw in the setups is that actually a VAE can be sometimes difficult to actually optimize on like more complex setups. Because what we have in a VAE, you have a prior loss, which basically tries to actually make sure that the latent space has not more information than it needs. But at the same time, you also try to actually put all of the information you can from the image into the latent space, because you need to reconstruct it again. So often these two losses are a bit competing with each other. So a way that we find to optimize much better is if you then separate the two. So you first train an autoencoder to just reduce your dimensionality to whatever you want. In this model is usually then perfect in reconstruction. And afterwards, you basically take this frozen autoencoder and apply instead a normalizing flow to take basically now a randomly distributed latent space to basically the latent space you want. And on these ones, you now apply your prior, and basically through the prior, you just learn now actually the causal structure you need. So this is just like a two-step that we often found to actually help to really make it more practical on complex environments. Okay, then let me also a bit show like experiments and how well it actually works. So as usually, we also started with like very synthetic environments to just show that it works and kind of a theory also is being seen in practice, but also try to now go actually a bit beyond to basically have here two robotics data sets that are already out in literature. So Causal World is here, for instance, where you have a tri-finger, which can interact in a certain space here, for instance, with different objects like a cube. And we perform the random actions. So you see basically an agent just doing random things with these three fingers, and some variables like the background and so on change with that. And then we also have an embodied AI environment, which you have seen already before in this presentation. So it's basically where an agent can do certain interactions, but we again have a random policy, and essentially we take the inspiration of a demo from this embodied AI environment where you can basically click on things and then interact through that. So essentially you assume the agent is just randomly clicking on an image without really knowing what it's doing. So let's start first with some synthetic environments. So essentially what we are doing there is just we randomly generate some causal mechanisms by randomly initialized neural networks. So these are then arbitrary nonlinear functions for the means. And we have like an additive Gaussian noise model to basically have like a more tricky setup. Usually we found if we basically use more complex noise models, actually most of the models start to work quite well. But with additive Gaussian noise model still is tricky because of this rotation invariance. And we generally found that BISCUIT is indeed like able to identify the causal variables quite well. So we report here the R2 score, which is like the MCC in terms of like permutation invariance and up to element-wise transformations. And we also test two setups where we basically on the one hand have like random interactions. So we basically actually have more interventions than we probably would need. And a setup where we now design specifically these interactions to have this minimum bound of interactions that we would need, like this log K that we have seen before. And in both cases, we actually see that the model performs quite decently. If we go beyond this bound, then we also saw that it breaks down because we don't fulfill all assumptions and don't have actually enough interactions to now identify our causal variables. The more interesting setup is now, for instance, this robotic setup, where we also actually now start to break some of our assumptions, because previously, we assumed that we have continuous variables, that things can also change, that generally we have a well-defined probability distribution between two time steps. But you see already here that we have a lot of deterministic relations. Like for instance, the cube, if nothing is happening to it, it doesn't really change its state. So you have actually like a deterministic distribution, which is not well defined if you now actually try to optimize it like with maximum likelihood. In terms of like actions, what we give the model is essentially just angle information of these three fingers. So it actually has to also figure out itself how these action information translates to this image of how the fingers look like. And again, if you compare it to other works, or also in general, we found that it works quite well in this environment to actually identify these different variables. And here it's also quite important to actually use this trick of an autoencoder with a normalizing flow. Because what we find is that if you have such a sequence and try to fit, like for instance, beta VAE, we ran basically a big grid search over 20 different values and basically a large range of a different beta. And usually it's quite tricky as long as you apply some regularization on the latent space. You usually are not able to identify like the things that heavily change and are quite small in the pixel space. So like, for instance, the cube here is quite small, especially if it's, for instance, here in the background, as well as the fingers, they are quite thin. So making a small mistake in localizing them in the image is actually breaking down very quickly. So here, using an autoencoder is quite important to compress all of the information you need in here. That?
So what are the causal variables here? It's the position of the cube and...
So we have a position of a cube, we have a velocity of a cube, we have a color of a cube, we have a color of the different fingers. There is friction on the ground, which is represented by also color. And we have basically the stage here as having different colors.
But so you cannot, so there is like this invertibility assumption, right? Where so from the image, you can infer the latence. So here from the image, you cannot really infer the speed of the cube, for instance, right? So I guess it's that's life, I guess. It still works.
I mean, yeah, indeed, it's a bit, so we first tested it without, like, yes, then of course you cannot find velocity, but we essentially add another channel to actually represent as like a frame difference from which you can then actually identify also velocity.
Okay, so you reconstruct not just the image, but like the delta also?
Yes, so
It's like
basically we
it's
add
like a
additional.
okay. It's like an extra channel that you have in your image, basically.
Exactly.
Okay.
Like if you would remove it, like I think what you could also easily do is just you don't train then like on a Markov assumption of just t-1 and t, but if you would actually do like t-2, t-1, and t, then you would not identify velocity, but you would be able to infer velocity from the previous frames to predict where the cube will be in the next frame again.
Got it. Yeah, makes sense.
Right, so this is basically just an example also where the autoencoder actually quite helps.
Yeah, actually, I have another question.
Sure, go ahead.
So do you so the size of the representation, does it match exactly the number of latents that you need to represent the problem?
No, we usually over-parameterize quite heavily. So I've for this one, I think like we use 32 latents, which is like 3 times the number that we actually would need. Like for the beta V, we also tested like going to 128 and similar to just see like basically what we usually find is that if you have too few latents, that's really where the performance is low. And then if you just increase the latents to a certain amount, at that point, it just starts to saturate. So if you give it even more latents, usually the performance doesn't improve, but it also doesn't decrease. So we usually have like a rule of thumb, like twice to 3 times as many latents as causal variables there are.
Okay.
And then do you find that you manage to get sparsity just by through the prior? Yeah.
Exactly. Just by the VAE, because any information that you would put in, you also have to predict again. So therefore, the model is actually interested in also not putting like more information than it would really need in there.
So quick question. So if when you evaluate, whether you have recovered the causal variables, do you is your model able to say, look, these are the coordinates where the causal variables are? Is it something that your model gives to you, or like when you evaluate, you sort of consider all the latents together and just when you do the matching, basically, right? Like when you evaluate, do you allow to search over all the coordinates, or your algorithm is actually like figuring out which of these coordinates are like the causal ones?
Yeah, that's a good one. So for the evaluation, we basically, for now, often assume that we can actually evaluate all of these latents. And we usually find that like most of the latents just have no correlation whatsoever with any of the causal variables. You could probably also find like a heuristic, like for instance, we could check our interaction variables. If they never change, if they are always constant, then there's a high chance that probably the model didn't use it. Or if you would check the marginal of these latents, we often found like they are just tiny and don't change. then you would also probably be able to infer that they don't carry information. But just to be like fully fair, like also for all the methods we compare to, we do the same. So we basically allow it to first search like which latents are actually the causal verbs or carry any information of them, and then we do the matching based on them.
Got it. Makes sense. Thanks.
One thing that I also want to show is basically what does the model actually learn in these interactions. So basically what we can do is afterwards also evaluate these interaction variables down here in the sense of, for instance, giving it the image, giving it the action, and seeing which of these interaction variables basically switches to 1 versus which ones are at -1. And what we compared it to is to like brown tooth interventional labels. So since this is a simulator, we can also still like find out actually when, for instance, the finger hits the cube, which is basically an interaction between like the robot and the cube. And what we find is actually that these match quite well. So the model is able to actually identify it up to a high, what we have here as a FR1 score. So especially interactions which don't depend on the previous time step, it's very accurate with. Like for instance, here the floor friction and the stage friction and so on. They had a certain mechanism that if the fingers, I think, touch with each other or similar, then you would have basically an interaction with it. But we have, for instance, if you have now the cube, it is a bit more tricky to be also fully accurate on that because the cube moves around. So you actually need to be quite precise in predicting from the previous time step, what are the causal variables and where exactly will be the finger and will it hit or not. So we sometimes find that just the model is slightly uncertain. So actually over predicts a bit the interactions with the cube. But it's still like actually quite decent. So since this is a F1 score and these interactions, I think happen like at 5% or less than 5% of the frames, it still gets actually a quite high recall and precision for the two. But of course, maybe like if you would supervise it now, it should be able to very quickly pick up on the ground truths. The second more realistic environment that I wanted to show is this embodied AI setting, where you have what we had here, basically a kitchen with also 10 causal variables that can change, like you can open the cabinet, you can take the egg, you can put it in the pan, then basically turning on the stove also cooks the egg. So you also have like several interactions. And I said before, basically what the agent gets is basically just the XY coordinate as its action. Like for instance, if you open the cabinet, then any region where the cabinet is shown in the picture, like any of the XY coordinates could be then the action that interacts with it. Again, like in terms of numbers, we are quite good in identifying these causal variables, but I want to show more like actually what can you do with it. And one thing that you can now, for instance, do, since this is like XY coordinates on your image, this action, we can again visualize in what locations actually the model predicts which latent variable will be interacted with versus which is not. So specifically, basically, if we take this as original image, what the model predicts that if we click anywhere in this left upper region, a certain latent, like the dimension doesn't really matter, but a certain latent will be then having a different interaction or will be interacted with, while if you would click around here, the model predicts that there will be no interaction. That's also quite close to like the ground truth we would imagine, since you basically, or this is basically also how we designed the environment. And for instance, in this microwave, you have two possible interactions where, for instance, if you click on the door, you would open it, versus if you would click on the control, you would turn it on, for instance. And similar, also the model would get that out, and you get actually quite nice segmentation in an unsupervised way with that. The only tricky thing that we found is especially like, again, these moving objects, since it depends on the previous time step, it's often less accurate actually in predicting interactions on these flexible objects, especially if they can be in multiple locations. So this is definitely something that could also be improved further. Another possible evaluation that we also often tried is actually to see if you can do compositional generation with it. So specifically, we're interested in, for instance, if you have a certain image, what if we now would, for instance, want to change just a certain variable in this image? And since we anyways kind of also assume that in a temporal space, all of these causal variables are conditionally independent, you would also not really have to worry about instantaneous effects. So basically, I could change the microwave without probably changing anything else. So for this, we would basically take a second image where these causal variables have been changed and probably everything else as well, and would both encode them and essentially combine in a latent space. So for this evaluation, for instance, we would assume we already have done like the MCC matching to see which latent variables probably correspond most to which causal variable. And then, for instance, take the causal variable of this image 2 that corresponds to the cabinet and replace them here with the latents of image 1. So basically just do like a inspection of these latents and would then decode the new image. And what we generally also see is that the model is able to generate these compositional generations. So for instance, if we take here an input image where the microwave is closed, we take another image where, for instance, many different variables have changed, but the microwave is open. If we just take the latent variable that the model identified for the microwave, put it into the latent of this image, you get out basically precisely the same state, except now you have changed actual microwave. And one also interesting thing that we found is that you actually also able to get outside of a training distribution and generate something that the simulator is actually not able to do. Namely that if you, for instance, intervene now on the stove on the front left, what we usually always see is that as soon as you turn on the stove, you cook the egg. That's what you see on the image on the right here. But actually here, since we force the state of the egg to be constant, so basically the state of the egg doesn't change in this compositional generation, we can actually now, for instance, turn on the stove without cooking the egg. And that's also actually quite curious because we don't have theoretical guarantees for it that the decoder also generalizes to that setup. But we found that especially with autoencoder, since it basically allows for like an arbitrary latent space, it's actually quite decent in terms of compositional generation, especially if the pixels don't fully overlap between causal variables. Question? Okay. Was there a question or? Okay. Otherwise, I will just continue. So the last thing that I just wanted to show is
Are you hearing something?
yeah, I think I hear Sarah. Do you also hear that, or is it just on my headphones?
I think it's just on you. We don't hear it.
From where is it coming? Okay, I don't. Okay, I will try to ignore it. That is weird. The last thing is basically here just the demo to show you a bit. Basically what we also took just the model in the Colab, and you can play a bit around. So we often see that it actually also is able to generalize quite further. So basically if you click things, then also that it interacts correspondingly. But the model also starts to break down if you actually now interact for like a long time. So for instance, if you click on the moving objects, then it actually has also a bit difficulties of predicting the next time step, simply because it is stochastic. So probably also a bit stronger model on the stochastic side would be helpful. With that, basically also, that's basically the conclusion a bit. That's, well, from the field perspective, we basically show that indeed, if you have this assumption of binary interactions, you can describe especially these interactions as well as finding the causal variables. And we find that it is actually quite applicable to some embodied AI environments, also if some assumptions are being broken by that. And that also gives me a bit of a hope that, like, from our theory, we can take it more as an inspiration often, like, for instance, why we should use a certain regularizer or similar in latent space, but it could be also more applicable beyond it. With that also, really just thanks also to my collaborators and just adding some references as well.
Thank you so much. That was great. Does anybody have questions?
I do.
Okay.
So basically I want to know, like, you know, your motivation for doing that. So, you know, so from what I understand, you know, this environment is I mean, by the way, it's super cool, right? Like I mean, it's the first time I see something you know, you know, tied to some real application, at least, you know, with these in terms of like this entanglement and causal variable. I think it's really cool. But I want to know, like, so, you know, for instance, to just get like good prediction, right? You could have trained just some like off the shelf variational RNN, or like, you know, some kind of generative model, you know, with actions, just to learn, you know, a model for these transitions without trying to extract the causal variables, right? Without trying to disentangle. So, you know, one obvious benefit of that is that you get something that is interpretable, right? You have these masks where you know, you can interpret, like, okay, when I click here, there's going to be like some interaction or something. So there's like this interpretability thing which is there, which is cool. But like, do you see something more to it than just interpretability? Like, what is the advantage of like disentangling variables like that apart from interpretability?
Yeah, that's a good point. So the main motivation for us was that we actually in reinforcement learning, there's also quite a field on factored MDPs. So essentially what this field often shows is that if you would be able to actually disentangle the state of, for instance, your environment into also different components, and knowing how you could actually differently interact with them without changing anything else, that can make your reinforcement learning agent more robust, more generalizable, and also generally actually work a bit better. So one of our hopes is also like on these specific environments, that now if you would use a reinforcement learning agent, you would actually have like this factored MDP setting, where probably the causal variables are like the closest that you would be interested in different setups. Of course, that is now up to assumption. And that this would help you to actually also be more robust and more generalizable. Of course, like it's at the moment still a bit tricky to go like end to end from it, because like these the other papers, for instance, use like sort attention or start already with like strong models like object detectors that already have like the inductive bias of like objects will be like the causal variables we care about. And then it's often hard to actually scale against them and make it competitive. But my hope would be that at least in some environments, it could be very helpful if you, for instance, don't know that the objects are like the causal variables you're interested in. And that on such a representation, a reinforcement learning agent would be now actually more robust to go beyond
it. I'd be curious to learn more about this factor MDP thing. I guess I'll read your paper. Did you discuss that in the paper quickly?
I think shortly, but not too much. Sarah has also other collaborations where she basically does a lot on like from the reinforcement learning perspective. If you would have affected MDP, how can you exploit it?
Okay. I guess I'll talk to her.
I have two questions, Philip. In this interaction maps image we're looking at here, if the causal variables were not disentangled, my guess was that these interaction maps, the segmentation wouldn't be quite as clean. Is that right?
Yes. We see that sometimes, for instance, like multiple moving objects are not fully disentangled. So it can be that some interaction maps, for instance, are the same for like the state of a plate here and the egg. So basically both of them, like the model both says, yeah, there's an interaction.
Okay, great. Maybe that's, I don't know if that connects to this factorization that you were talking about with MDPs, but that also seems kind of beneficial, right? Like having some sparse connectivity between interactions and like parts of the image that they're localized to.
Yeah, and you can also be now more sample efficient, right? Because now, for instance, you know that if you click around here in this image, nothing will happen anyway. So your agent will not be really interested in just clicking around. And if you would, for instance, now have a reward signal, you could also try to track back actually which causal verbals influence even the reward signal.
Yeah.
And if you, for instance, are just interested in cooking the egg, you're not interested in opening the cabinet 5 times because it anyways doesn't influence it.
Yeah, it's cool. I was really just surprised, or not surprised, but I think the compositional generalization results that you showed, they just seem kind of magical. Like, why did that happen? Because this was with the normalizing flow-based version of BISCUIT, right? So how did the decoder kind of seem to get imbued with this kind of compositional structure?
Yeah, that's a good point. And also, like it's still not fully clear to me, but generally what I see that if we train an autoencoder, if causal verbals are already disentangled in pixel space. So for instance, if one object is always in the left upper corner and another object is always in the bottom right corner, often the autoencoder already starts to separate them in latent space. It generally starts to actually have more of a relation of like pixel location and what I need to know from it. And in this specific case here, while basically the egg and the stove burner are close by, still like there's no pixel overlap. So both of them, the autoencoder starts to already be like not fully disentangled. So we still see the latents are entangled, but there's probably actually an easier map between the two. And that gives me currently intuition why that actually works quite well. If you now have causal verbals that overlap a lot in pixel space, I would doubt that this would be possible as similar here.
Very cool. Really interesting.
So do you see this just by doing reconstruction, or you do also like VAE style reconstruction? Like, do you have a prior here, or like?
So here we actually don't have any prior. So the
Okay,
reconstruction loss is just the MSE, and the latent space. The only thing that I sometimes do is like I apply a small L2 equalizer to not let the latents go like to 20 or 100, but usually it doesn't even need it.
Do you think like just by training a reconstruction we would get something like this on this data set?
I mean, at least that you could get like this or compositional generation, because this is exactly like we trained just the autoencoder on this data set and then disentangled the latents from the autoencoder space. I would not now say basically that in any data set, in any combination, that would be fully working.
Of course.
But I also have a feeling that maybe, for instance, what in your work of additive decoders, I have a feeling that probably this model already learns implicitly multiple additive decoders in that sense. And if it does, then you also generalize through that.
Mm-hmm. So yeah, I'm just curious, like what's the magic ingredients that makes the thing somehow additive here? It's kind of surprising.
Yeah, that is also something still to investigate.